human heart is an engineering marvel, a powerful, self-regulating pump that keeps us alive by circulating blood throughout the body. It does this using carefully timed electrical signals that coordinate the contraction of its chambers. If you ever watched a medical drama or visited a hospital, you've likely heard the iconic beep associated with heart monitors. This sound comes from an electrocardiogram, or ECG for short. In this video, we will explore how we can harness the power of machine learning to interpret these ECG signals, training a model to classify heartbeats with performance exceeding that of expert cardiologists. An ECG records the electrical activity of the heart over time, mapping voltage against time. Each heartbeat generates a distinct waveform that corresponds to different phases of the cardiac cycle. The P wave marks the electrical activation of the atria, causing them to contract and push blood to the ventricles. The QRS complex represents the electrical activation of the ventricles as they contract to pump blood to the lungs and the rest of the body. The T wave indicates the recovery of the ventricles as they electrically reset in preparation for the next beat. However, what makes ECGs particularly interesting is how much information they reveal about the heart's health and rhythm. For example, an elevated ST interval indicates a blockage of one of the heart's main supply arteries, leading to a heart attack. Similarly, peaked T waves and diminished P waves are hallmark signs of abnormally high potassium levels in the blood. Since ECGs are commonly used to check heart health, hospitals often have trained staff called telemetry technicians who watch these signals closely. They usually monitor several patients at the same time, looking for signs of heart problems. But doing this for many patients at once can be tiring and stressful. That's where AI can help. We can train a computer model to recognize different types of heartbeats from ECG signals. This model can quickly scan the data and alert doctors or nurses if something looks wrong. Unlike humans, AI can go through large amounts of data in just seconds and does not get tired or distracted. If trained well, it can be very fast, reliable, and helpful in keeping patients safe. To train an AI for this task, we need a large and reliable data set. For this project, we use MIT BIH Arrhythmia Database, a well-known collection of ECG recordings. It contains 48 half-hour ECG signals recorded from 47 different people between 1975 and 1979. Each ECG recording is pre-processed so that the voltage values are normalized between 0 and 1, and every sample contains 187 data points, representing a short window of the ECG signal. Each sample is also labeled based on the type of heartbeat. The labels include normal, supraventricular ectopy, beats which start in the atria, ventricular ectopy, beats which start in the ventricles, fusion, beats which come from both the atria and the ventricles at the same time, and unknown, beats where the origin is not clearly defined. The dataset is heavily imbalanced, with normal heartbeats making up over 3/4 of all samples. While this can present a challenge during model training, it also reflects real-world conditions, where normal heart rhythms are more common than rare or unknown ones. To evaluate the performance of our machine learning models, we first introduce the confusion matrix. This is a square table where each row represents the true class and each column represents the predicted class. The values along the diagonal of the matrix represent the number of correct predictions for each class. For example, how many normal heartbeats were correctly identified as normal. With the confusion matrix, we can define two more metrics to evaluate model efficiency. The simplest metric is overall accuracy. It measures the total number of correct predictions divided by the total number of samples. In this confusion matrix, overall accuracy would be 12 plus 10 divided by 12 plus 10 plus 1 plus 2, or 88.0%. While useful, this metric can be misleading if the dataset is imbalanced, like in our case, where normal heartbeats make up the majority of the data. A model could achieve high overall accuracy just by correctly identifying normal heartbeats while failing to detect rarer and abnormal ones. To get a better picture of how the model performs across all classes, we use the per-class accuracy. This is calculated by taking the mean of the diagonal elements of the normalized confusion matrix. In this example, it would be 12 divided by 12 plus 2 plus 10 divided by 10 plus 1, or 88.3%. This way, each class contributes equally to the accuracy, regardless of how many samples it has, making the per-class accuracy especially useful for imbalanced datasets. Now we will introduce the implementation of various machine learning architectures. The goal of this section is to simply get you familiar with the concepts behind how they work. The first machine learning model we use is the support vector machine. This model tries to find a boundary, called a hyperplane, that separates different categories of data. Ideally, all points from one class should fall on one side of the hyperplane, and all points from the other class on the opposite side. The best hyperplane is the one that maximizes the margin, which is the distance between the hyperplane and the closest data points from each class. These closest points are called support vectors, and they are critical in defining the boundary. However, in many real-world problems, including ours, the data can't be separated by a simple straight line. To handle this, the support vector machine uses something called the kernel trick. This technique transforms the data into a higher dimensional space, where it becomes easier to find a linear boundary. Once the boundary is found in this new space, the model then projects it back to the original space, resulting in a nonlinear decision boundary that works well with the original data. scikit-learn, a popular machine learning package, implements all of these in the SVM module, which we call to train on our dataset, making sure to use the radial basis function for the kernel trick. We find that the support vector machine gives an overall accuracy of 96.802% and a per-class accuracy of 76.362%. Looking at the confusion matrix, we can see that the model excels at predicting normal and unknown ECGs, but is bad at predicting supraventricular ectopy and fusion ECGs. One way to improve this performance is to add decision-making capabilities to our model using random forests. Let's start with the idea of a decision tree. A decision tree works by asking a series of true or false questions about the input data. These questions help split the data into smaller and smaller groups until each group contains mostly samples from a single class. In other words, it tries to sort the data into pure subgroups. A random forest is simply a collection of many decision trees, hence the name forest. Each tree is trained slightly differently and given its own prediction. When the model sees new data, all trees cast a vote on what they think the class should be. The class that gets the most votes becomes the model's final prediction. This ensemble approach reduces errors and usually leads to a more robust and accurate prediction than a single decision tree. scikit-learn implements all of this in the random forest classifier module, which we simply call to train on our dataset. We find that random forest improves the overall and per class accuracy to 97.433 and 80.539% respectively. Looking at the confusion matrix, we can see that these gains come from improvements in all classes. One way to further increase predictive accuracy is using deep learning, specifically a convolutional neural network, or CNN. CNNs automatically learn hierarchical features directly from raw input signals, which have been shown to be especially effective for spatially structured data like image classification, or time series data such as our ECGs. CNNs are composed of several key components that work together to extract and interpret patterns in data. First, convolutional layers apply filters, or kernels, that slide across the input to detect local features, such as characteristic waveforms and ECG signals. The kernel size determines the receptive field of each filter, with smaller kernels focusing on fine-grained details and large kernels capturing broader contextual features. Because this operation will reduce the spatial dimension of the signal, extra pixels are added around the border of the input to preserve the size in a process known as padding. After each convolution, the leaky ReLU activation function is used to calculate the output of the node given certain inputs. This activation function is chosen as it introduces nonlinearity into the model, allowing it to learn more complex patterns. These outputs are then normalized to recenter them around 0 and rescaled to a standard size so that we can accelerate training. Neural networks, however, are prone to overfitting, or memorizing training data, which leads to poor performance on new, unseen data. To combat this, a fraction of the neurons is randomly deactivated to learn more robust representations. Finally, a kernel slides over the input and outputs the maximum value within each window in a process known as max pooling. This decreases the size of the signal, which helps preserve only the most important features while discarding the less important ones. This process, kernel filtering and padding, activation, dropout, and max pooling, is repeated 5 times to extract necessary features from the ECG. After feature extraction, the output is flattened and passed through a fully connected or dense layer, which combines the higher level features learned by the convolutional blocks and performs the final classification. The output is a one-hot encoded vector of length 5, where the index corresponding to the predicted class is set to 1 and all others to 0. You may have noticed that the number of parameters we need to choose are increasing, which includes the size of the kernel and padding, activation slope, fraction of neurons deactivated in dropout, and kernel size in max pooling. One way to choose these parameters is setting limits on each of them and creating a grid to try each combination. This search, known as grid search, would take very long. The next thing you might think of is randomly picking points on the grid and running only a few trials, saving the parameters with the best results. Although this reduces computation time, it's not very efficient. Thus, we use Bayesian optimization, which builds a probabilistic model to focus the search on combinations that are most likely to improve performance. By combining these carefully tuned components, the CNN can effectively capture local waveform patterns and long-range temporal dependencies in the ECG signals. This is verified by the increase in overall and per-class accuracy to 98.762 and 93.038% respectively. From the confusion matrix, we find that these gains mainly come from improvements in predicting supraventricular and ventricular ectopy beats. Another interesting analysis we can perform with the CNN is the TSNE projection. This allows us to peer into internal representations learned by the network and observe how it separates the data by class. Initially, we find that the raw input data is highly entangled, with samples from different classes overlapping significantly. However, after training the CNN, the learned feature representations become much more structured as data points from the same class form tight, coherent clusters. The last boost to predictive accuracy involves creating an ensemble model. Here, we combine predictions from all 3 classifiers: the support vector machine, the random forest, and the convolutional neural network. Each model contributes to the final decision through a weighted voting scheme, where predictions are assigned different weights based on the model's performance. This ensemble approach leverages the strengths of each model and often leads to improved overall accuracy compared to using any single classifier alone. After tuning the voting weights using Bayesian optimization, we find that the ensemble model relies primarily on the strong performance of the CNN, with a smaller contribution from the random forest classifier. The support vector machine receives almost no weight, indicating it contributes little to the final decision. As a result, both overall and per-class accuracy improves slightly to 98.776 and 93.041% respectively. In previous studies, expert cardiologists have been shown to achieve per-class accuracies ranging from approximately 78% to 83%. In contrast, our final model surpasses this benchmark, achieving a per-class accuracy of 93.041% after less than 10 minutes of training. This highlights the remarkable efficiency of machine learning systems which can match or exceed expert-level performance despite cardiologists undergoing 14 years of education and clinical training beyond high school. If deployed, which is a process we will discuss in an upcoming video, this model would require an incoming ECG to be pre-processed in the same format as used in training and testing. Currently, the model is capable of classifying heartbeats into 5 categories. However, the full spectrum of clinically recognized arrhythmias is nearly twice of that. Expanding the dataset, particularly with an emphasis on underrepresented and rare arrhythmic events, could significantly enhance the model's generalizability and clinical relevance. In a real-world application, we might see this model intervene in a situation when a tired telemetry technician is unable to identify and take action on a life-threatening rhythm to save a patient's life. All code used in this work is available in the GitHub repository linked in the video description, along with all the reference citations. If there's a specific topic you would like me to dive into, please drop a comment below. I always enjoy hearing from the community, and your feedback helps shape what comes next. If you found this content valuable, don't forget to like, share, subscribe, and turn on post notifications so you don't miss future uploads. Thanks for watching, and I'll see you in the next one.